Alright, we are finished with the moment distribution process and have come to a reasonably converged answer to the member end moments, and now we're going to turn this back into shear and moment diagrams and a qualitative deflected shape. So let's recall that we've got positive is clockwise, so the end moment here is 285.2 going counterclockwise on the member end. We have an applied load of 80 kilonewtons per meter, and we have an end moment that's really close to zero, but it is positive at about 1.5. We do have a slight little difference here in these two member end moments that I'm going to ignore because I don't want to write the average down of 1.45. I could. I'm just going to be a little lazy about that because I don't want to deal with that kind of precision. So I'll just take what we've got, and noting that the presumption is that you end up with then the effect that if you make a rounding error in one place, that somewhere else you'll probably have made a rounding error in the other direction. So then the big picture things will actually work out okay. And so we've got all our member end moments and applied loads that are then shown, but we don't have any of the member end shears to have that are present either. So let's go get those. That our left hand shear is going to be acting upwards, I think, and so we've got then 285.2 going in a counterclockwise fashion, plus 80 times 5 for the load times 2.5 for its moment arm, and minus the 1.5 that is out here at the far right. And so then we divide by the length of the member for the moment arm for that shear, and that'll be 256.7 kilonewtons for that shear. We could subtract off 80 times 5, or 400, and we get 143.3, but I'm going to go ahead and just do the math again, or summing moments about the other end. 80 times 5 times the 2.5 plus now 1.5 minus 285.2, and divide by our length. We get 143.2 again. Like it, or well, really 143.3, let's call it. Likewise, in the middle, we have a net of 119.8 minus 1.4, divide by 7.5 for that member length. So we get 15.8 for those two shears. And let's see, this net trying to go in a clockwise fashion, so that means these shears will have to be like so. I'll write all the shear values above the axis, and then probably we have shears going in this direction on the right hand span, and so we've got 119.9 plus 100 times 5 times 2.5 for the moment arm, minus the 252.5 at the other end, divide by, then that positive means it's going counterclockwise, divide by our 5, and we'll have 223.5 for that end shear. In the other direction, we have 100 times 5 times 2.5 plus the 252.5 minus the 119.9, and divide that by 5. You get 276.5 plus the 223.5. That equals 500 and change, which is what it should, to get equilibrium in the vertical direction. So it looks like we're pretty close to being correct there. All right, so now let's go do the shear diagram. And let's see, 256 and 143, so let's establish that roughly as our scale. There's 256.7. It's going to linearly decrease to 143.3. While we're at it, we might as well go figure out where that transition is happening. 256.7 divided by 80 will be 3.21 meters to get over to that location. That will be helpful. Heck, we're right here right now. We might as well get this area. That's going to be the change in moment. 3.21 times our 256.7 divided by 2 is a total net change of moment of 411.8 minus the 285.2 that's going to be on that left end. So for a positive of 126.6 right here, where we started off at minus 285.2, right, and that'll be second order going down, maximizing right there. And since again we're right here, we might as well check our math. 5 minus 3.21 would be 1.79, so 126.6, let's just put that in memory. 1.79 times 143.3 and divided by 2 would be a minus 128.25 plus what we have in there, and we get negative 1.6, so really close to where what we have said that it's supposed to be. So close to zero that by scale you wouldn't even see it, so I'm going to show it like that. And we'll get out the little handy French curve to try to get this in here in a somewhat reasonable qualitative fashion. Our inflection point will be somewhere over in here. In the deflected shape, we'll handle that in just a little bit. And that looks like that's not unreasonable for that second order curve. Let me pull that all the way up better so you can see that. Okay, that's that span. The next one's a little bit quicker to do. We go down 15.8 and then we'll come over flat at 15.8. So there really won't be much of a change here. Well, not much of one. There isn't any change on the shear diagram. And on the moment diagram, we'll go straight from the 1.4 or 1.6 or negative 1.5, whichever one you like here, and it'll end up at 119.8. Let's just check that out. This was 15.8 and change. It was really 119.8 minus the 1.4 divided by the 7.5. You know, we're just sort of going in a circular direction here, because then I'm just going to multiply that by 7.5 again. There's your net change. Now we're going to get back to the 119.8, in other words. It's all going to agree because, of course, it's all based upon exactly the same numbers. Being all negative here in the middle does mean that we have nothing but hogging curvature here in the middle. That's kind of interesting. And we get out here to the far right, and let's do the shear diagram again. We'll pop up to a positive 223.5, and at 100 kilonewtons per meter, that means at 2.235 meters over, we're going to cross zero. We're going to get all the way down to 276. And again, that will be 2.235 meters over there. Right, and then of course that closes off the shear diagram. Moment diagram, of course, we're going to end up with an not an inflection point, but rather a maximum right over here at 2.235 meters over. And so we'll have 223.5 times 2.235 divided by 2 for that area. So that's net area is going to be 249.76 minus the 119.9-ish that we started at, or about 129.9 will be our net positive here. All has just a little tiny bit of rounding error in it, and then you'd subtract off what we've got going on over here, and 276.5 negative divided by 2 equals that, plus there, and sure enough we end up at 252.5 or 4, right around right where we're supposed to be. There again, we'll come along and we'll get our French curve, draw this around in a nice second order type fashion. Right? You know, when you're drawing these by hand, which is all, you know, that's precision enough. We do care about these moments at other locations. If you're familiar with steel design, you know lateral torsional buckling and the CB coefficient. We have to go find things at quarter points and midpoints of the bracing pattern, but to establish a lot of interesting aspects of the strength there. But notionally is what we're really interested in at this particular time. Right, so now we go look and we say we got negative curvature here in the middle. That means the only way that can fit in there is, you know, something of this kind of nature. We've got frowny face, positive face, frowny face, so looks to me like we're going to have something that nearly zero rotation here, or even at joint C probably a clockwise type rotation to ever begin to try to make this work. And the inflection point is relatively close to the support, but maybe we have something that looks like that in the middle. Right? At the far ends, both far ends, we have negative moment, so we're going to go ahead and get that in there. And likewise over here, we're not being super precise about where that inflection point is located. We're just noting generally where it's got to be at. And of course at joint B, the moment is nearly zero, and so that inflection point is essentially right on top of that joint. And what we find out, even though this is all qualitative, that even though the applied load was, let's improve this slightly, applied load was the largest out in that right span compared to the left hand span, and you might think the deflection would be bigger, the impact of the support movement is very significant. Pulling this down is going to pop up this right hand span way over distant. Okay, its effect would, if we had multiple spans as we went along, would get smaller and smaller, but there's these ripple effects. In this case it looks like that the support movement does actually have quite a bit of an influence on the overall performance of the system.